MotoGP bikes are now heavily influenced by aerodynamics, with teams adopting ideas from Formula One and aerospace design. Features like winglets and diffusers have transformed modern machines. Recently, a detail on the Aprilia MotoGP bike sparked speculation that it may use a concept similar to Formula One's F-Duct. If true, it could reduce drag on straights while keeping downforce in corners. But is that really the case? The origin of the F-Duct idea. To understand the speculation around Aprilia's design, we first need to revisit the technology being referenced. Back in the 2010 Formula One season, McLaren introduced the F-Duct, a clever aerodynamic system that allowed drivers to stall the rear wing on long straights. When the driver covered a small duct opening with their hand or knee, airflow inside the car was redirected toward the rear wing. This disrupted the airflow across the wing surface, effectively reducing drag and increasing top speed. When the driver removed their hand from the duct, normal airflow returned, and the wing produced full downforce again. The system was brilliant, but controversial. It required drivers to physically block a hole in the cockpit while driving at more than 300 km/h. After one season, the FIA banned the concept because it was considered unsafe and too complex. Now, some observers believe Aprilia may have adapted a similar idea, but applied to a MotoGP bike, the curious rubber duct on the Aprilia. The discussion revolves around a small but noticeable feature on the Aprilia race bike, a rubber duct located near the rider's arm position. The theory is that the rider can unintentionally, or perhaps intentionally, close this duct with their arm during high-speed sections of the track. When the duct is blocked, the airflow through the system changes. When the rider moves their arm away, the duct opens again. This behavior has led some people to speculate that Aprilia created a MotoGP version of the F-Duct, a system that alters aerodynamic performance depending on whether the duct is open or closed. At first glance, the concept seems plausible, but the real aerodynamic picture may be far more complicated. The proposed diffuser stall theory. One explanation circulating among analysts suggests the following. Air enters the bike through small inlets near the front of the fairing. These channels guide airflow internally toward the rear of the machine. Under normal circumstances, that air exits through a specific outlet near the diffuser area. However, if the rider blocks the duct with their arm, the airflow cannot exit in the same way. Instead, it would be redirected downward toward the diffuser section on the side of the bike. In theory, this redirected airflow could stall the diffuser, reducing aerodynamic load and decreasing drag on straights, exactly the kind of advantage teams look for in MotoGP. The diffuser itself is located along the lower side surfaces of the bike's aerodynamic bodywork. It includes small vertical elements called strakes, which help guide and expand airflow underneath the fairing. This creates a low-pressure region that generates downforce. If that airflow were disrupted or stalled, the diffuser would produce less aerodynamic resistance. In other words, the bike might become slightly faster on the straights. But there's a problem with this theory. Why stalling the diffuser might not make sense. Some analysts doubt the diffuser stall explanation. On Formula One cars, F-duct systems require visible outlets where air exits to disrupt the wing's airflow. However, on the Aprilia bike, those clear exit points are not visible, making the theory harder to support. Additionally, on long straights, the airflow around the bike is relatively stable, meaning the diffuser isn't under the same stress as it is in corners. Because of this, stalling the diffuser on a straight might not provide much benefit. So if that theory doesn't fully add up, what could Aprilia actually be doing? Cooling aerodynamics. A much more practical explanation relates to cooling airflow management. MotoGP bikes generate enormous amounts of heat. Radiators, oil coolers, and electronic components all require continuous airflow to maintain safe operating temperatures. On most bikes, the cooling system sits directly behind the front wheel. Unfortunately, that location creates a serious aerodynamic problem. Air entering the radiator area slows down dramatically and then exits the bike through large vents along the side fairings. These vents release hot air, but they also create drag. In aerodynamic terms, the cooling system behaves like a parachute, slowing the bike down. This is where Aprilia's duct system might come into play, controlling cooling flow on the straights. The ducts visible on the Aprilia bike appear to run from the front of the fairing toward the rear side sections. These channels could serve as alternative pathways for radiator airflow. When the ducts are open, cooling air flows freely through the radiators and exits the bike efficiently. This would be ideal during slow sections of the track where engine temperatures rise. But when the rider blocks the duct with their arm on the straights, the exit area for cooling airflow becomes smaller. That reduces the amount of air moving through the radiators. With less airflow leaving the bike, there is also less aerodynamic drag. The result? Slightly higher top speed. This explanation aligns with a basic aerodynamic principle. Reducing cooling airflow reduces drag. Evidence from performance data. Interestingly, Aprilia's MotoGP machine has already demonstrated strong straight-line performance. During testing sessions, the bike reportedly achieved top speeds slightly higher than some competitors, roughly 1 km/h faster in certain measurements. That difference might sound small, but in MotoGP, even a single km/h can be significant. At the end of a long straight, that extra speed could provide the advantage needed to attempt an overtake or defend a position. If the duct system truly allows the bike to slightly reduce drag on straights, it could be a clever engineering solution. Front wing aerodynamics. There is also another interesting possibility. The air inlets appear to sit directly behind the bike's front wing elements. These wings generate aerodynamic load on the front wheel, helping prevent wheelies during acceleration and improving corner stability. However, wings also generate drag. If the air ducts behind the wing are open, they could help extract airflow from the wing's surface, improving its aerodynamic efficiency. But if the rider blocks the ducts with their arm, airflow into the system stops. This would effectively create a larger obstruction behind the wing. In aerodynamic terms, that could cause the wing to produce less downforce and less drag. Again, this would be beneficial on the straights where maximum speed matters more than cornering stability. Why MotoGP aerodynamics is getting so complex. Aprilia's duct system reflects a bigger shift in MotoGP engineering. In the past, racing focused mainly on engines, chassis design, and rider skill, while aerodynamics played a smaller role. Today, that has changed dramatically. Modern MotoGP bikes now use winglets, side diffusers, ground effect bodywork, and advanced cooling airflow systems. Manufacturers are essentially treating these machines like miniature Formula 1 cars, where even small aerodynamic gains can improve lap times. The challenge of rider-controlled aerodynamics. Unlike Formula 1 cars, MotoGP bikes include a rider who constantly moves around the machine. That movement can actually influence the bike's aerodynamics. A rider's body position can block or expose vents, change airflow around the wings, and alter pressure zones around the fairing. Engineers can potentially use these movements to create dynamic aerodynamic effects without relying on electronic systems that might break the rules. Aprilia's duct system could be one example of this innovative approach. Innovation within the rules. MotoGP regulations tightly control aerodynamic development. Any design that gives teams a performance advantage without breaking the rules becomes extremely valuable. If Aprilia has indeed developed a passive system that slightly reduces drag on the straights while preserving cooling efficiency in corners, it would represent a clever piece of engineering. Even if the gains are small, they could make a difference in a championship where races are often decided by fractions of a second. The real answer may remain secret. Ultimately, only Aprilia's engineers know exactly how their aerodynamic ducts work. Teams guard these innovations carefully, and competitors spend months trying to reverse engineer each other's designs through photos, wind tunnel analysis, and data. What looks like a simple rubber duct could actually be part of a far more sophisticated airflow system hidden inside the bike's fairing. Until more evidence emerges, the debate will likely continue. But one thing is certain: MotoGP aerodynamics is becoming increasingly inventive and increasingly mysterious. And if this system really does offer even the smallest advantage, you can bet the other manufacturers are already studying it very closely. And that's what makes this Aprilia aerodynamic mystery so fascinating. What do you think Aprilia is really doing here? Let me know your thoughts in the comments. And if you enjoy deep dives into motorsport technology like this, make sure to like and subscribe for more videos.